So in this second piece of lecture one, we're going to talk about beam equilibrium specifically and how translational and rotational equilibrium help us understand what's going on outside a beam externally to support it. We use that to figure out what we call reactions, the forces within a beam's supports that enable it to stand up. And then in week 2 lectures, we'll go in and we'll use that what we learned to figure out what happens actually inside a beam. But we need to establish what holds a beam in place, how we figure out the external forces on it, and sort of make ourselves fluent in that so that we can then accurately and reliably go ahead and start to do beam design. So we'll talk in this video just about the principles behind beam equilibrium. And then the last couple of videos, we'll do some examples. And we'll look specifically at the difference between point loads and distributed loads when we're trying to figure out reactions. But for this lecture, just principles, vocabulary, a few thought experiments to figure out how to keep beams stable in space. So we have 2 tasks when we're designing any structural element. The first is that we have a series of external conditions that are being put onto our structure. And we have to figure out how to make the beam actually stable, keep it from falling down, keep it from tipping over. And then we also need to figure out what happens within the beam and figure out ways to use the material we have to hand to make it strong enough and stiff enough for it to be serviceable. So if you think about this beam, right, one that maybe is a familiar situation to you, there are external conditions that our body has to resist when we're doing a plank. And the external condition really is mostly our own dead weight, right? We're carrying our own weight over the span of our height. If you think about it, we're going to have resisting forces in the floor that are going to push back on our feet and our arms. And clearly, the sum total of those has to be equal and opposite to our body's own weight. But we also have to think about how that weight is distributed, not only to keep us from falling down, but also to keep us from falling over. So what's the balance between the two that enables us to stay upright and not fall over one way or the other? Maybe more apparent to us are the internal stresses, right? And this is what we'll get to in the next set of lectures. What happens to our abdominal muscles, to our back, to our thighs, to our shoulders? We can feel very clearly how a beam works when we're doing a plank because of the various muscles that get sore. What we're going to talk about in this video, though, are mostly what we feel in our toes, and in this case on our elbows, right? The forces in the floor that are pushing back, and how to think about those so that we're keeping our own self stable. Every piece of a structural element obviously needs to be in equilibrium. We don't want one floor that's falling down or one column that's falling down. So as we're looking at a building structure, we're dividing it into elements: slabs, beams, girders, columns, foundations. And at every step of the way, we're trying to think of the external forces that are going to be required to make the element stable. So we have forces like live loads, dead loads, people, books, boxes of cookies, whatever. Those forces are being put, for instance, on the floor slab. That floor slab has to be supported in a way that is equal and opposite to the loads that we're putting on it. We also, of course, have to take into account the dead weight of the slab itself. Those external reactions, the things that are supporting the floor slab, have to not only be equal and opposite, they have to hold the building up, keep it in translational equilibrium in the y direction, but they also have to be arrayed in such a way that the floor isn't rotating, right? Isn't falling over one way or the other. And figuring out the distribution of external resistance is the way both to figure out how that slab is stable, but also to get into what the slab has to be experiencing internally to resist the loads that we're putting on it. So here's one way to think about it, right? When we're talking about beam equilibrium, what we're doing is we're taking the load that we're putting onto a beam, in this example, 5,000 kilogram train, and we're figuring out the loads in the reactions that will support it. And if you look at this, you can see that 3750 and 1250 is equal and opposite to 5,000 kilograms. So we have translational equilibrium in the y direction. We don't have any horizontal forces. We're not, in this case, apparently taking into account wind or earthquakes. But if you look too, you'll notice that those two reactions, the 3750 and the 1250, are arrayed in such a way that they balance one another out around the locomotive. What do I mean by that? We'll get into an example where we think about a beam basically as an upside down seesaw, and we'll look at what we call the moment arm of each of those reactions and figure out how they can balance out so that the bridge is not only not heading straight down, but also not rotating. Later on, we'll talk about internal equilibrium. What has to happen within the fabric of a beam to make sure that that every piece of it stays stable, and that we don't have, as you see in the bottom slide here, a failure where the beam is actually breaking or sagging. Right? Those are all internal equilibrium issues that we will get to. First, we have to figure out how the beam is stable or is stabilized from its external loads and reactions. We're going to look at two things. One is the sum of all the vertical external forces. So the loads that we are putting onto a beam in particular, minus the reactions that are able to support the beam. And we want the total sum of the forces acting downward and the forces acting upward, obviously, to equal 0. The slightly trickier thing is to remind ourselves that we also need to stabilize a beam rotationally. So the sum of all the external forces that are trying to rotate the beam also have to equal 0. Vertical forces are fairly easy, right? Up minus down. When we're talking about rotational forces, we're talking about the sense of the forces in a slightly different way. We're talking about clockwise versus anti-clockwise, right? Forces that are going to tend to spin the beam basically to the right, forces that are going to tend to spin the beam to the left. And those two have to equal 0. The issue is that it's not quite as simple as just summing up the loads. We also have to take into account where those loads are on a structure. So, okay, let's look at a classic seesaw as a way into this, right? A seesaw we can think of as a beam that has a slightly odd support system, right? It has one support in the middle, and the loads are the things that we can move in or out, away from, closer to, or further away from that fulcrum. We can think about the seesaw, of course, as a lever, and we can talk about the leverage that rider 1 and rider 2 are putting onto the seesaw around that fulcrum, right, around the point at the middle. That leverage is also called a moment force, or just a moment, sometimes called torque, and it is simply the force that we're putting onto the system times its distance away from any given point. So here we're particularly interested, of course, in the fulcrum, since it's a lever. And if you look at the seesaw, we can figure out fairly quickly that the seesaw is going to be in translational equilibrium. Rider 1 weighs 200 pounds, that's going down. Rider 2 weighs 100 pounds, that's going down. We have a force in the fulcrum that is resisting that's going to be equal and opposite to their combined weight. So 200 pounds on the left plus 100 pounds on the right equals 300 pounds. And if you come down here, you can see that we have 200 going down, 100 going down. That's being met by 300 going up. Translational equilibrium, very easy to solve. All we need is a fulcrum that's capable of resisting 300 pounds across its cross-section. We can make that out of steel, concrete, marshmallows, whatever. All we have to do is know how much stress, how much compressive stress that material is capable of supporting, and then we have to multiply that by an area until we get to 300 pounds. Right? Fairly simple. Rotational equilibrium is a little bit difficult. We know that we have to think about not only how much each of those riders weigh, but where they are in relation to the fulcrum. Think about it like a wrench. Right? If you have a very, very short wrench, you have less leverage over the bolt that you're trying to undo. If you have a very, very long wrench, you have a lot more leverage. So what's going on in this situation? Well, we have two very, very different loads, right? One is twice as big as the other. If, in fact, we want the seesaw to balance out, we have to locate them on the seesaw in a way where each of their weight times the lever arm that they have around the fulcrum is going to be equal to one another. So in this case, we have a 200-pound rider, and we've put him 5 feet away from the fulcrum. We have a 100-pound rider. We've put her 10 feet from the fulcrum. Now, if you think about this, we have the force, that's their weight, times the distance around, or distance from the fulcrum. That is the distance from where the center of their load to that point there. Those two have to be equal and opposite. This rider has to put a moment or lever arm or a leverage, onto the seesaw that is equal and opposite to rider 2. The way we've done this is we put the 200-pound guy 5 feet from the fulcrum. 200 pounds times 5 feet is going to be equal and opposite to 100 pounds times 10 feet. They'll both be 1,000 something, and if you think about it, that'll be in pound feet, or we more often say foot pounds. And if you think about it, they're also going in the opposite direction. What is rider 1's weight doing to the seesaw? It's trying to spin it around anti-clockwise, counterclockwise. What is rider 2 trying to do to the seesaw? Her position is such that her weight and lever arm are trying to rotate the seesaw clockwise. So they are going in opposite directions. Both of them are inducing a moment or a torque leverage around the fulcrum of 1,000 foot-pounds, and therefore we can say that the seesaw is going to be in equilibrium. Here it is in slightly more mathy forms. We have the moment force for rider 1 on the top, 200 pounds, that's the rider's weight, 5 feet, that's his distance from the fulcrum. 200 times 5 is going to be 1,000 foot-pounds. And for our purposes, we'll say that's a negative moment. We can decide which direction is positive or negative, clockwise or counterclockwise, doesn't matter so long as we're consistent. So, okay, we're saying that a counterclockwise or anti-clockwise moment is going to be negative. So rider number 1 is putting 1,000 foot-pounds of counterclockwise moment onto the system. Rider number 2 weighs 100 pounds. Her distance from the fulcrum is 10 feet. And so she too is putting 1,000 foot-pounds of moment onto the seesaw, but notice that it's positive. She's going in the opposite direction, clockwise. And so long as these are equal to one another, so long as they're going in opposite directions, we know this from experience, maybe a while ago for some of us, heavier person close to the fulcrum, lighter person farther away from the fulcrum, we can get to a point where the two moments are equal and opposite, and the seesaw will balance perfectly. And here are the two ways that we look at that, right? Here's the load condition, 200 pounds, 100 pounds, and here's the way we'll diagram that, right? The two loads, the resisting load here, and then moments going in equal, moments that are equal to one another, but with opposite sensibilities, right? Counterclockwise versus clockwise. And here we can say that this seesaw is in translational and rotational equilibrium, successful structural element. So how does this help us? Well, we can flip that seesaw over, right? And we can think about having a load that needs to be supported, supports that hold it up. We'll dive into what the beam is actually doing in the next set of lectures. And we can use the same principles of the quantity of load and the distance of that load from a given point to figure out the moment forces that would have to be equal and opposite to keep the beam from rotating, and then use those to start to figure out how the beam is going to actually bend. So if you think about this condition here, this guy is very, very close to one support, very far away from another support. If we flip that over and think about it like a teeter-totter, we have a fulcrum that's way over on one side of the seesaw. We have a reaction here that's going to have to be quite large, a reaction here that's going to be quite small to balance things out. If the person is sitting in the middle, we can imagine that the loads are going to want to be pretty much equal, right? The moments going in either direction want to be equal, their moment arms are equal, therefore the forces will want to be equal. We want to sum up the vertical forces, we want to sum up the rotational forces, and everything really wants to equal 0. We want 0 in the y direction, we want 0 in the clockwise or anti-clockwise direction. Can't fall down, can't rotate. What we need to know to do this, when we looked at the Seesaw, we had to know the loading conditions. We had to know the span, or the distance that each one of our riders was from the fulcrum. We had to know the position of those loads. We certainly had to know their magnitude, how much they weighed. And then the support conditions, we had to know where the fulcrum was, and we had to know what type of support it was. If we know all of those things, and we'll go back to those again and again, we can first solve for the reactions at the supports. That's what we're going to do in the next video. We can use that to figure out where the beam is undergoing the most amount of shear, where it's undergoing the most amount of bending. We'll do all this in the next lecture. We can then come back. We can use those figures to figure out the shape and size of the spanning member, and then we can use that to calculate the amount of deflection that we're likely to experience. We will get into those concepts. We'll look at sort of flipping the seesaw over, where the loads become the support becomes the load. And in the next video, we'll do some examples that show how that seesaw principle, along with what we need to know about the conditions of the supports, can help us actually, through a little thought exercise, figure out what the reactions have to be on a given load with a point load on it.